Let's try the first applications of derivatives problems from Paul's online notes. Click on Applications. And the first link we have is rates of change. So let's just work through a few examples. Please read this website yourself. Let's look at example 1. Determine all the points where the following function is not changing. So we have g of x is equals to 5 minus 6x minus 10 cosine 2x. We punched it into Desmos here. And this looks like some kind of sinusoidal graph that's decreasing, going downhill. So the idea where the function is not changing means that it's not increasing nor is it decreasing. And so the key idea here is that you have to think about when the slope is 0. So just looking at this purple graph here, you can see that the graph is not changing here, which is a maximum. It's not changing here, which is a minimum. And there's a maximum, there's a minimum, not changing here, and it keeps on repeating. Between this interval where my mouse is going up and down, the purple graph is increasing left to right, and it's decreasing left to right over here. But when we say not changing, we're talking about the slope or instantaneous rate of change is 0. So literally, we're talking about g of x, but on Desmos we just type in y is equals to, or f of x equals to, same thing. We're talking about the same function here. And if we're to focus on the derivative being 0 is the key. So I'm going to use Desmos' shortcut here. I'm just going to type in f prime of x. And without actually calculating what the derivative is, you can see the derivative here is negative 6 plus 20 sine 2x. We can very quickly know what the answer looks like. So let me just hide this purple graph. Or let me just show it actually. So we're focusing on the slope being 0 right here. So I'm going to click on the black graph here is the derivative graph of f of x. When the slope is 0, we're talking about the maximum. 1.418 is the x value. So let me just hide that for a sec here. Click on the purple graph. Click on the maximum. You can see that 1.418 is definitely going to be a position in which we have a maximum in which the function is not changing. So we can verify answers using Desmos. Now let's just use algebra here. The derivative of 5 is nothing, it disappears. The derivative of negative 6x is going to be negative 6. And then here, the derivative of cosine of 2x is going to be negative sine of 2x. Look up at your formula sheet. Times chain rule times 2. So you can see what happened here is I'm just going to focus on this part here. And so the derivative of this is going to be negative 10. I'm just working on this last term here. Times derivative of cosine is going to be negative sine of the angle. But don't forget that we need to multiply by the chain rule, the derivative of the inside here. Derivative of 2x is going to be times 2. So as you can see, that this becomes a negative 2 multiplied by negative 10 becomes positive 20. And this is going to be sine 2x over here. That's how Professor Paul figured out what the derivative was. Okay, so we're definitely setting this derivative function to be 0 to get these maximums and minimums. And what's happening here is we're going to simply throw the negative 6 over. We're going to divide by the coefficient 20 here. 6 divided by 20 is 0.3, and we have sine of some angle is equals to 0.3. So if, for example, we let theta is equals to 2x, if I say sine theta is equals to 0.3, how do you figure out what theta is? You could use the quadrant system here. ASTC, sine is positive in this quadrant. So use your calculator in the radian mode. And so if you hit the sine inverse button to get the angle, you get theta is equals to sine inverse of 0.3. we get the reference angle. And we have a 0.304. So 0.304 radians is quite small. You can even convert it to degrees if you want to know exactly where it is. But it's around 17 degrees. It's going to be 0.3047 radians. And then to get the second theta value, this is theta 1. To get the second angle, it's going to be pi, which is half a turn, minus that same value. So theta 2, so theta 1, we just figured out it's going to be approximately 0.3047, and theta 2 is going to be pi minus that. So pi minus that value is around 2.84. So I'm going to say 2.8369 radians approximately. And you can see it's over here. Now when Professor Paul writes 2x equals that amount, that 2x is your theta. Okay, so we have these different answers respecting the different quadrants, the possible values of theta. We're going to divide both sides by 2. So instead of 2x, now we have x. And this general solution for trigonometry is 2 pi n. We have an integer n, which respects the fact that we have revolutions. And the 2 pi is one full rotation. When we divide by 2 across this whole equation to 2 pi, now becomes a pi. Okay, so here we have the solutions.